So thank you, everybody, and thank you for listening to me today. So I think it was really nice to give a presentation on cemented carbides. So I will try to do that today and going ahead all the way from microstructure to applications. For those of you who don't know, cemented carbides is a powder metallurgical material. So you start by mixing powders and then spray drying them, pressing them, and then subset them to liquid phase sintering. And the sintering temperatures that are usually used are between 1380 and 1500 degrees C, so quite high temperatures. And the typical sintering time is between half an hour to 1 hour up at sintering temperature. Let's see. No, I can't. No, where's the arrow there? The microstructure of cemented carbide is, as you can see, it's a composite material, and it consists of tungsten carbide grains. Can you see my pointer? I guess these are the white grains in this image. And then the cobalt binder, which is the gray phase in this image. And as you can see, the grain size of the tungsten carbide grains is quite small. It varies from around 0.2 microns up to 15 microns, and it's selected depending on the application. The smaller the grains, the harder the material you get, and the larger the grains, the more ductile. But compared to steel power-based materials, the grains are very small. And as you can see also here in the image, the tungsten carbide grains, they are very faceted in their shape, and we will come back to that. For typical applications such as rock drilling and metal cutting or wear parts, the ductile cobalt-rich binder, the gray phase here, is usually between 5 to 16 volume percent. So the majority of the material is tungsten carbide. Here. During the liquid phase sintering, the cobalt-rich binder melts, while the tungsten carbide grains are still in the solid state. But what happens during when the cobalt is melted is that you have a rapid grain growth of the tungsten carbide grains. As you saw, the grains are faceted, which means that the growth of the grains are really limited by the 2D nucleation and coarsening of the grains. And the shape is called today a truncated prism, as you can see here down to the left. And the growth is limited by the formation of the nucleation of a new layer on each plane and the growth of that layer when it's nucleated. If we look at the crystal, it consists mainly of two types of planes. It's the basal plane, because the tungsten carbide crystal is hexagonal. But it's something important to remember, even though it's hexagonal, it has a C to A ratio that is very close to 1, which is very unusual compared to other carbides with the hexagonal structure. And you see here is the basal plane, and these two planes are called the prismatic planes, and you have two different prismatic planes depending on the termination of the carbon atom. So a question then you can ask yourself when you try to design the microstructure: is it possible to govern the tungsten carbide grain shape, as it's so important when it comes to the applications for this composite material? As you saw then, you have these two different planes. And if we also do it by liquid phase sintering, and if we start with the liquid phase sintering and the phase diagram, it is in this region you would like to be after sintering, which is the tungsten carbide phase and the cobalt binder phase. And as you can see here in the phase diagram, the melting temperature decreases with an increase in carbon. You can also see that the carbon window here is very, very narrow. If we continue to this, then you can see that you really would like to be in this area of the phase diagram, because if you're to the left of this point, you will form something called an interface, which is a brittle phase. And it's very unlikely that during the cooling process, if it's nucleated in the liquid, that it will be time enough to back transform to tungsten carbide and cobalt. And also, if it does so, then you will have a local microstructure non-uniformity inside your material, which leads to locally different properties there. So this is something you would like to avoid. So that is why you would like to be in this gray area of the phase diagram. If we look at the phase diagram again up at sintering temperature, and now looking at the ternary section at 1410 degrees C, this is the area phase field for the cobalt liquid, and this is the tungsten carbide stoichiometric crystal. And thus you would like to be in sintering temperatures in this two-phase field. However, remember now that we have usually very little cobalt in our materials, so we are actually up here. And then you can see also how narrow the carbon region is up at sintering temperatures. But that is not enough, because you also need to be you need to be here, of course, to avoid interface and graphite. But it's also important that after cooling, and we usually say that we freeze the mobility of the tungsten atoms in the binder phase at 1000 degrees C. So then you need to be in this region. And as you can see here at 1000 degrees C, the carbon range is even more narrow compared to up in the liquid state. Still, you must be able to come to this point in your final microstructure. If we look at the cobalt liquid, of course, the properties and the growth of the cemented carbide depends on the carbon activity. And here is the two-phase field, and here you can see the line that is between the eta phase, that when you have a carbon activity of approximately 0.3, and the graphite limit, where we have a carbon activity of 0.1. And depending on if you are at this point or at this point, it will actually affect your final grain shape of your tungsten carbide crystal. And that is what we will speak about in the next, and now focusing mainly on the tungsten carbide distribution, grain shape, and binder composition. So, first, as said, cemented carbide grow a lot during sintering, and one work that has been done to understand and how to translate the 2D grain size to the 3D grain size by modeling has been done using a so-called inverse Saltykov method, where it was modeled by Jeppsson and co-workers and then verified by 3D EBSD by Ida Borg. And this model then for transferring the initial distribution of the tungsten carbide grains to the final sintering distribution is really good and coherent. However, in this modeling, the grain shape was originally not taken into account. So since we know that we have different surfaces, we also started to take that into account into the coarsening model. And this was done here by Mannesson, but later also by Bombalev, and we will come back to that later on. In this case, when we looked at the coarsening model, then we found out that when we took into account the grain growth of the tungsten carbide crystal, we needed to have a model for the nucleation of a new plane. And at the same time, we learned that the dissolution of the shrinking grains, in that case, the best agreement between the experimental values and the model was when we didn't have any limit on the dissolution of the shrinking grains, but we had it on the growth of the growing grains. If we come back to the shape and the carbon activity, here in these pictures, you can see that when we are sintering and when we have equilibrium with graphite and the carbon activity of 1, then we will get very triangular grains, sharp grains like this. While if we have equilibrium with the eta phase and thus a carbon activity around 0.3, we will get more equiaxed grains, as you can see here in this image and here. And you can also see that they are more truncated at the corners compared to when we have equilibrium with graphite. To understand this, we did, together with a group in Gothenburg, we did ab initio calculations and looked at the ratio between the basal and prismatic planes, as you can see here. And we then compared theoretical values to experimental values measured by TEM. And of course, then this is TEM statistics then. And here you can see that we got a fairly good agreement. So it seems to be that we actually, at the graphite limit, then favors the basal plane and on the crystals. And if we try to then draw this to scale, you can see here at the graphite limit we have larger crystals compared to when we are here. And also that actually here, even if it's difficult to see in the image, but the prismatic planes are a little bit higher compared to here in this case. However, the question is of course, how is it in between? Because this is in the extreme cases of eta phase limit and graphite limit. And in normal production material, we would like to be in between. So then we started to do an investigation about that. So we placed one in the eta phase and one in the graphite and 3 different alloys with carbon activities in between the extremes of 1 and 0.3 to study the grain shape of the tungsten carbide crystals. And here you can see the eta phase and the graphite, and this is as published. And this is the repetition, this is the eta phase, and you can clearly see here that the grains are more equiaxed, and you can see the growth steps here, while this is on the graphite limit where they are more planar and triangular. So if we come to then the in-between, and here are the alloys that we made in between. And first and foremost, you can see that the average radius is not perfectly linear between the eta phase and the graphite limit. There is a change here in the average radius as measured by EBSD. And if we look into the microstructures, and here we have etched away the binder after sintering, and here you can see the 3 alloys that are in between. So this one is close to the eta phase limit, and this one is close to the graphite limit, but not in the graphite limit. And you can see here that in this case, actually we have quite equiaxed grains still. And in this case, we have planar facets, but not as planar as for 1, but they are still more triangular. Here in between, they are larger, but they are more equiaxed compared to the planar triangular grains that we have in the graphite limit. So the question then is, of course, if you remember, it's not just the carbon activity that varies in this case. If you remember, we also had a different melting point of the cobalt binder, with the melting point being lower for the graphite sample, which means that the higher the carbon activity, the longer time in liquid, and that can of course also contribute to the grain shape and the grain size. So in order to study that, we also sintered the same samples for 5 hours to see the impact of, so that the time when we heat the sample would be small compared to the time up at sintering temperature, and thus the relative difference in melting point would be small compared to the time in the liquid. And in this case, you can see that when it comes, of course, they have all grown, so they are larger, but the shape of the grains are more or less the same as it was after 1 hour of sintering, with these two being more equiaxed and this one starting to be more triangular when you come to the graphite limit, but still not as triangular as the one on the graphite limit. And this is very important because the tungsten carbide crystal is a hexagonal crystal and it's anisotropic. So it's much harder in one direction compared to the other. And here is an overview when you can see the effect of the sintering time 1 hour top and 5 hours, and also the difference in carbon activity between for the different materials. And as you see, these two start to get more triangular compared to this. So this is just a summary and conclusion of the impact of the carbon activity on the grain shape of the tungsten carbide microstructure, where you have more equiaxed grains close to the interface or up to approximately 0.6. And then you have a non-linear increase in the average grain size with increasing carbon activity. And this is then, when it comes to the grain shape, it seems to be independent of sintering time. And there is no large difference in grain shape between 0.6 and 1. But this, as said, more equiaxed on this side. If I continue with the next, then I will now turn over to interfaces in cemented carbide. And this is, as you can imagine, I think you have it. If you have a small grain size, as we have between 0.4 and 400 nanometers up to rock drilling grades that have around 3 microns, 4 microns sometimes in grain size. But still it is small, which means that a lot of the microstructure is really phase interfaces and interfaces. And the most typical ones are tungsten carbide interfaces between the tungsten carbide grains. And the other type of interface is the tungsten carbide cobalt interface. And here is a high resolution image of a tungsten carbide cobalt interface. And of course, all these interfaces coupled to the microstructure is what in the end will give the material properties. If we look at the interfaces, here is a tungsten carbide grain and a tungsten carbide grain in an F10 image. And it shows that cobalt has segregated to this tungsten carbide grain boundary, as you can see here in the peak. And experimental and today also ab initio calculations predict and show that it's approximately half a monolayer of cobalt in a tungsten carbide interface. And when we started this, it was a question, can it be found by atomistic calculations? And today we know that it can. can other elements also segregate to the tungsten carbide grain boundaries? And if they do, what is the effect of the segregants on the interfacial properties? Because that in turn will have an impact on the final microstructure and the properties of the final material. So here in this graph, you can see on the top, you can see the willingness to segregate to a tungsten carbide grain boundary. And of course, it's several bars here, depending on the termination of the boundary, of the atoms and the boundary. But as you can see, cobalt wants to segregate. And here you can see that also manganese and chromium wants to segregate among the material we have done the calculation on in this case. Here you can also see the segregation energy for different materials. So why does this matter? This matters, of course, that if we can have an impact on the strength of the tungsten carbide interfaces, we can also design materials that would require a higher force to separate the grain boundaries, and thereby, for instance, make materials that are less prone for plastic deformation. And by saying that, it's so that plastic deformation in cemented carbides, in addition to, of course, dislocation movements and so on, also is done by infiltration of cobalt or lamellas in the tungsten carbide grain boundaries. And that is something we will see later on in the presentation. So if the elements segregate then, what is the effect on the strength of the boundary if they do? And here you can see that both on the tungsten-rich tungsten carbide interfaces, you can see that both chromium, manganese, and cobalt are strengthening the interface on the tungsten-rich interfaces. On the carbonate-rich interfaces, almost all seem to strengthen the interface. So if we look at tungsten carbide interfaces, there are random interfaces and there are also special ones. And the special ones are called sigma 2, twist, and tilt. These are low energy interfaces, and they are quite frequent in the tungsten carbide material. And you can see them here in red. So if since the sigma 2 or these special low energy interfaces are very strong, they are more likely to be intact during deformation, since they have a higher fracture barrier and are lowering the driving force for infiltration. And here the arrows shows that what happens instead is that you form binder lamella in the microstructure when the microstructure is deformed plastically, and those are indicated by the red arrows here. And here is a comparison of the frequency of lamellas between undeformed and deformed material and the sigma 2 values of the special boundaries. And here you can see that in the deformed material, the special boundaries have a higher frequency than compared to the undeformed. And this is, of course, because these lamellas do not preferentially form in the strongest boundaries, they form in the weakest boundaries. And in this case, you can see a comparison where here in the red, here you can see red, I put some arrows. These are the special boundaries. And this is the corresponding image of the microstructure. So what is the impact? In cemented carbides, you often want to inhibit the grain growth. So what is the impact of different grain growth inhibitors like chromium and vanadium on the amount of sigma 2 boundaries? And in this case, we also included manganese, which is a very uncommon addition in cemented carbide. But since it was predicted to increase the strength, we wanted to include it. And this is the reference. And here you can see, of course, that they are grain growth inhibitors. So without an inhibitor, you have about approximately 0.7 in average grain size. And with vanadium, 0.4, and chromium, 0.67, so not as much here. And manganese, almost no effect at all. But if you look at the fraction of the sigma-2 boundaries, it's interesting to see that compared to the reference material, both the vanadium and the chromium material had a much higher fraction of sigma-2 grain boundaries after sintering compared to the reference. If we look at inhibitors like chromium, we can here compare the black phase diagram, which is without chromium, with the green, which is with an addition of 0.43% weight percent of chromium. And you can see that the chromium lowers the melting temperature of the liquid. Despite this, if you start from exactly the same raw material and sinter it under the same conditions, this is the impact of chromium on the microstructure. So this one is without chromium, and this one is with 0.43% chromium. And then I've also tried to draw the different shapes of the crystal here, exaggerated, but into scale, so you also can see how the addition of chromium and the addition of carbon, so carbon, higher carbon to the right, is affecting the grain shape and the distribution or the fraction of basal to prismatic planes in the crystal. If we continue looking at the interfaces, and in this case we made an exaggerated sample adding the double amount of chromium, which is approximately 10% of chromium in the binder or 1% addition. This is in atomic percent. And then here you can see the TEM images. This is the tungsten carbide crystal. And here you can then see that along all the tungsten carbide cobalt interfaces, you see a layer of something. And when we looked at this in higher resolution, or Sabine and Aurélie Delanoë, who was the PhD student, we saw that this is actually 0.3 nanometers, or 3 nanometers, sorry, of a cubic chromium tungsten carbide. And it grows epitaxially on the tungsten carbide crystal, which means that with an addition of 10% of chromium in the binder, you are actually modifying all the phase interfaces in your entire material. And this also, as you will see later, has a huge impact on the properties and was something, of course, that we needed to patent at that time. But here you can see then this layer. You can also do measurements of chromium in cobalt. So you can, if you do it in the bulk of the binder here and take the chromium to cobalt ratio, it's approximately 4.7. While at the interface here, the ratio is much higher, it's 6%. Further, we did atom probe studies then of the segregation of chromium to the interface. And here you see tungsten carbide grain and the binder phase in an atom probe sample. And here you can see the chromium atoms here in pink. And if you go here close to the interface and make this proxy diagram, you can see that the chromium is clearly increasing here at the interface. And if you look carefully, you can also see that the tungsten goes up at the same time as the chromium goes up, which means that this chromium layer is, as we saw in the TM images, on the growing epitaxially on the tungsten carbide crystal. So it is a mixed tungsten chromium carbide at the interface, because you can also see here how the carbon goes up at the interface. Later on, this been studied, or later many studies, this was also observed with vanadium, but in case of vanadium, it's instead a layer of a vanadium carbide, the cubic vanadium carbide here. And the difference between chromium and vanadium is that for vanadium, the vanadium carbide is thermodynamically more stable than the chromium carbide. And this was observed by Yamamoto first time in Japan. Further studies showed also by Sabine Ley that there is a layer, small layer, when you have smaller additions of vanadium, also at the interface of the tungsten carbide crystal. And today we know also that you get a cubic layer, but of a tungsten carbide, cubic tungsten carbide actually, when you are lowering carbon on the basal plane. So the question when it comes to vanadium is we know that vanadium is a very powerful grain growth inhibitor, but is it due to segregation of vanadium to the interfaces, or is it due to the nucleation of a layer at the tungsten carbide cobalt interface? I would say this is still an open question, but we will try to share some light on it as we go on here. If we look at the atom probe results, we can clearly see that the vanadium in this case is also increased at the interface. And also in this case, the carbon and the tungsten increases at the same time as vanadium increases. And here is a comparison then between the calculation of the composition using thermocalc on the vanadium tungsten carbide and the measurements by atom probe. So the question is it really a thin film formation, or is it a segregation? And here in this article by Sugiyama, they think that it's could actually be both. So they think that at low carbon you will have a layer on the basal plane and on the prismatic plane, while at high carbon contents you will have a layer hindering the growth of the basal plane, but on the prismatic plane you will have segregation of vanadium, which then would lead to different shapes of the tungsten carbide crystal depending on if you are on low and high carbon, also for vanadium. So we tried to look at this a little bit to see if we could understand this, combining lots of different types of investigations, so both modeling and grain growth coarsening. So here you have the relative tungsten carbide grain size as a function of the vanadium addition. And you can see how it dramatically decreases the tungsten carbide grain size as the vanadium addition increase. And in this case, we also tried to model the grain growth and using both coarsening by segregation to the layers and the interface mobility. And then we tried to see how much of the driving force were actually taken up by the nucleation of a layer and the growth of a layer. And this is very interesting that it seems as depending on where you are, so this is a little bit in agreement with the Japanese article, that depending on where you are in the carbon activity, a larger part of the driving force is consumed by growing the interface compared to the nucleation. I would say that this is something that we are still working on and trying to understand a little bit more in detail. Something that is also of impact, of course, is also the temperature. When we do this, we constructed something called interfacial phase diagrams, combining the ab initio calculations with thermodynamics. because the ab initio calculations show that you could have this layer of vanadium carbide, for instance, even at levels of vanadium that was lower than the solubility limit in the phase diagram. And then by combining ab initio calculations with thermodynamics, we could predict when we would have the layers and when we wouldn't have the layers. And here you can see in this diagram, you have the bulk precipitate here. And in this region, you will have layers of vanadium tungsten carbide. And you have the temperature here on the y-axis. So you must keep in mind that you can actually walk or change the conditions from having a layer not to having a layer, just also by altering the temperature. And here we studied, a lot of co-workers here studied by TM, it was Prasad, I think, and the interfaces after sintering in this vanadium doped material, where you can see that the vanadium carbide definitely has segregated to the basal plane. Here to the prismatic plane, well, think so, but well, I think we still have a little bit more work to do here in this case. So, thin film segregation, well, low carbon layers and high versus at high carbon, we probably only have the layers on the basal plane when it comes to vanadium. But it also depends on, of course, the vanadium content in relation to the tungsten carbide grain size, and in turn also the stoichiometry of the vanadium tungsten carbide. But it also depends on the sintering temperature and where you are in the interfacial phase diagram. So I would say that this is where we are when it comes to understanding the grain growth inhibitors. And we now continue a little bit on interfaces. So there are also other cubic carbide formers than vanadium, and I will especially speak a little bit about titanium. And here you can see the reference and the impact on the grain size. And you can see that also titanium is a very effective grain growth inhibitor. Here you can see the microstructure of a titanium tungsten carbide material that also has titanium tungsten carbide, the middle gray phase, precipitated. So we are at titanium saturation levels at all temperatures. And this is the reference. If we look at the atom probe results, we can see that also in this case, we have cobalt and titanium at the interface, and titanium is in purple. But what looks a little bit interesting is that the titanium don't seem to be random. And it's even more obvious when you look at it in this way. So we are looking at this tungsten carbide interface, and here's the cobalt atoms, and here's the titanium atoms. And if we look at this, these atoms are actually at every 17th layer, which corresponds to the misfit dislocation at the interface between tungsten carbide and cobalt, which is interesting. If we look here, we can also see here as an increase in the titanium amount at the interface between the binder and the tungsten carbide crystal, and also in this case, as for vanadium, the carbon and the titanium increases at the same point. If we look at the other interfaces in this material, like titanium vanadium carbide and tungsten carbide, we also here find cobalt segregation at these interfaces in the material. And here we go back again to looking at the titanium to the interface between cobalt and tungsten carbide in the material with titanium additions above the solubility limit. And in this case, here a high resolution image of the interface. we can see titanium atoms in dark here, and here you have the titanium atoms. And if we look at this even more in detail, we can see here that the titanium atoms are actually at every second layer. So there's a layer of tungsten carbide here at the very end of the interface. And we are now looking at the basal plane of the tungsten carbide crystal. So this is a summary. So if we look at the tungsten carbide, and tungsten carbide gamma phase boundaries, cobalt, titanium, niobium, zirconium, and chromium segregate to these grain boundaries. Tantalum is not observed to segregate. Cobalt segregates to tungsten carbide gamma phase interfaces. Cobalt segregate to tantalum carbide grain boundaries. So, if you look at tungsten carbide cobalt phase interfaces, these elements segregate to these, and segregation of vanadium corresponds to approximately one monolayer of close packed vanadium carbide, in the case we looked at here. Segregation of titanium, chromium, manganese, zirconium, and niobium and tantalum corresponds to a thin film with a thickness smaller than one monolayer, assuming a cubic B1 MC structure. And titanium and tantalum segregate to tungsten carbide cobalt phase boundaries, and it's not completely verified whether niobium and zirconium segregates to the boundary. I will now shortly just show how this has an impact on performance. Of course, if you look at these materials, you now realize that this materials is really a lot of phase interfaces and grain boundaries. And this will, of course, in turn have an impact on rupture and bend strength, grain boundary sliding, and plastic deformation. If you remember this, you can have segregations to the grain boundaries, and that can also strengthen the interface or weaken the interface. When we do use our materials in turning, for instance, we can get plastic deformation, as you see here, where this edge of this insert has turned down during turning because it can't last the heat any longer. And here is just an illustration of the stress strain curves in this case. If we look into the material, we have heavy plastic deformation of the tungsten carbide grains with slip bands and two different activated slip systems. If we also see the formation of low energy boundaries where the tungsten carbide grains are in contact. And this is now for a reference, a non-doped material. We can also see that a lot of the plastic deformation is facilitated by formation of this type of lamella. So it's a layer of cobalt that goes into the generic tungsten carbide grain boundary. And it also happens for cermets that you can see in this case. So we try to understand this plastic deformation, and here you can see the reference geometry and the geometry after it has been deformed. And you can clearly see that the temperatures as modeled by FEM calculations are really high, so 900 up to 1,000 degrees in this area of the material. You can also here see a cross-section of the geometry of the plastic deformation and before plastic deformation. And here is the magnitude of the in-plane shear stress in the cross-section. We can see that you have a large amount here of in-plane shear stress, which corresponds to this point of the insert. And here you can see that this is a tungsten carbide grain and this is a tungsten carbide grain. And here you can see a lamella formation clearly shown here in the image. And in this case, it was turning with an alternative binder cemented carbide. So that is why you can see iron here and nickel. If we then wanted to know this lamella formation, is that just a coincidence or is it really true? So then we did investigations of the lamella density. Here in this graph, you can see the distance along the edge from the previous slide. And in light gray, it was the lamella density of an insert that had not been upset for turning or plastic deformation. While the black one, it was in a case where you had done turning with the and got the plastically deformed insert. So you can clearly see that there is a huge difference in the amount of lamella formation as a function of the plastic deformation. You could also see cavity formation in areas where the plastic deformation was so rapid so that the material cannot accommodate for the temperatures and the forces, and it resulted in cavity formation instead. And here you can see the lamella density in zone B, which was here in this insert. So you have zone 1B here and zone 5B here. And you can see then in zone 1B after for the nickel cobalt and for zone 1B for a cobalt reference and zone 5B, and you can see that there is a huge increase in zone 1B compared to zone 5B in this case. And the same when it comes to cavities, that it's much more. So why is this important to understand this? Then, of course, if you understand this, you can also start designing your materials. And that is what we have done here for a rock drilling application. So here you can see a cemented carbide with undoped that has no additions at all, just tungsten carbide, and a cobalt, and the other one, which is a tungsten carbide chromium material. And here we have done high temperature creep under compression at the 1000 degrees C. And this is what the rod looked before and after testing. And here you can see the deformation or the strain, how the strain, there's a temperature here on this axis, and the strain, since it's compression, it's negative. And this is the cobalt-based material without any addition. And it took around 900 seconds to reach compression of -10% in strain. While with the chromium, and you saw the layers at the grain boundaries, the increase in strength of the tungsten carbide grain boundaries, suddenly it took over almost 2,500 seconds to reach 10% of deformation under compression at the 1000 degrees C. And here you can see the same going up to 19 or 17% of deformation, where it took around 1,100 seconds without chromium addition. And in this case, when we have the layers, it took around 3,400 seconds. And this is actually used today in the Sandvik mining rock drilling products. And of course, it's patented all around the world. And now recently published for those who would like to read more. And what we think is that the mechanism that is causing the creep is actually this lamella formation and the grain boundary accommodation. We found the same phenomena with the increase in growth of the tungsten carbide grain perpendicular to the loading direction, and thus a decrease parallel to the loading direction. But we observed actually the same type of phenomena after testing in both material, but it looks like the kinetics is totally different and thus hindered by these interfacial layers around the crystals. And with this, I would just say thank you.